I saw that you wrote okay, so well, maybe welcome everybody to the second lecture of this this mini course. So I saw yesterday, Hendrik, that you put this a very nice reference page after your your notes. I will try to do the same as well. So I did that at the first page, so I won't forget about it. So what I want to do today is I want to explain you this how this relative entropy method works. So as I was telling you yesterday, there's especially in analysis they do this what they call entropy method. In general is that they define these convex functionals to get a priori bounds on solutions of evolution equations. And after they get these a priori bounds, they can do more sophisticated stuff like regularity improvement, etc. And but in our case, also our goal is to describe these non-equilibrium stationary states. We don't know this explicitly, this non-equilibrium stationary state, so we need to do something different, because we cannot use as a baseline this as a reference measure for this, for example, for the relative entropy, the non-equilibrium stationary state. Okay, so one way to overcome that is what is called the relative entropy method, what was invented by Yao in the context of hydrodynamic limits of interacting particle systems. So so if you want to take a look at how hydrodynamic limits are obtained using this relative entropy method, you can take a look at the book by Kibnis and Landin. And what I'm going to present now is taken from my my paper with Octavio Meneses. And so the basic idea is that you want to use as a reference measure something which is not the invariant measure in your Markov chain. So you have so let me maybe go to the general context. So I just remind you about the setup. So the setup is going to be completely general. So I'm just taking any finite state Markov chain. Okay. So let me call omega the state space, xt the Markov chain itself, r are the jump rates, L is the generator that I defined yesterday. I'm not repeating here the formula. So I'm going to assume that the chain is irreducible. Otherwise, we just look at a minimal substate of the chain, and I'm going to call mu the invariant measure. I'm going so mu, yeah, mu was the invariant measure, and gamma was the carré de Champ. And the idea now is that we don't want to use the measure mu in any explicit way, because in principle we don't really know it, and that's the guide for which we want to have obtain information. Okay, so what we do is that we fix a reference measure nu now, and this reference measure, so I'm going to assume that it has full support. So this, in general, I'm going to call a measure a reference measure. A probability measure is going to be a reference measure if it has full support. Okay, and then I'm going to fix a differentiable family of reference measure mu t. So differentiable means differential with respect to t. So it means that actually mu t of x is differentiable as a function of t for any x on the state space of the Markov chain. And then I'm going to define some density functions. Okay, so the first thing is phi of t. So phi of t is the Radon-Nikodym derivative of the reference measure mu t with respect to the to the base reference measure nu. Okay, and the idea is that this psi of t is going to be explicitly computable because we are going to choose the measure nu and the measure mu t in such a way that we can compute this this psi of t. That's of course in the computations where I'm going to present is not necessary, but when you enter into applications of this relative entropy method, that's the whole point, that psi of t is actually something computable. And then I'm going to define f of t as the density of the law of the process at time t with respect to the reference measure mu t. Okay, so in particular, for example, ft times psi t is the density of the law of the process at time t with respect to the base reference measure nu. Okay, and we are going to use the entropy, relative entropy, as our convex functional to measure distance between measures in omega. And in particular, I'm going to call h of t the relative entropy of the density f of t. Okay, notice that this is computed with respect to mu t. Okay, and of course you can rewrite it as this, the integral of ft log ft with respect to psi t times d mu. Okay, so and actually when we do computations, we use the second interpretation, at least for general computations. The first interpretation is will give us some probabilistic intuition about what we are going to do. So now the Fokker-Planck equation is slightly different from what I presented last time, because it's not ft what satisfies the Fokker-Planck equation, because ft is the density of the law with respect to a moving reference measure. Okay, so actually ft times psi t is the one that satisfies Fokker-Planck equation, because that is that product is actually the density of the law of the process with respect to the fixed reference measure nu. And here, something nice about the Fokker-Planck equation is that it is always true, even when the reference measure is not invariant measure of the Markov chain we are considering. Okay, in that case, what happens is that the adjoint operator L star that appears in the Fokker-Planck equation is adjoint with respect to L2 of the base measure. So in this case here, this L star is different from the star that we discussed yesterday, because we are taking now the adjoint with respect to L2 of nu. And we have to observe that unless nu is the invariant measure of our Markov chain, the operator L star is not going to be a Markovian operator. Okay. In particular, L star of a constant is not equal to 0. And this is something to we have to remind, because it's going to appear in a few lines. Okay, so now what is Yau inequality? Okay, so Yau's inequality is this inequality here. Is that the derivative of the relative entropy, so of the density ft, is less or equal than a negative term, so which is given by the Carré-Duchamp. So it's the same term that we found before, plus something else. No, so sometimes this is called entropy production term, and the entropy production term is the expectation of a certain function ft, which is given by this formula down there. Okay, so here there are various things that we have to understand about this inequality. This inequality is very interesting because it has various nice interpretations. And those are the ones that I want to discuss now. The first one is that this expectation of the function ft, it can be written in two different ways. Okay, it can be written as an expectation, or it can be written as an integral with respect to the measure mu t. Okay, so you can write it at ft times the density little ft integrated with respect to the measure mu t. Okay, so here, if you want to, after you write down this inequality, and this is actually was the point of view of Yao when he introduced the inequality, you say, okay, from now on, I can completely forget about probability. So this is somehow in the spirit of what Henry was saying, you know, that somehow we want to separate probability from analysis. So arriving to this inequality, we just use the probabilistic arguments with Markov chains and etc. And if you're willing to, here we can forget about completely. We can forget completely about the probability and stick to the second interpretation, that this expectation is just the integral of ft with respect to ft mu. And now we have a sort of this inequality turns into a variational problem. Okay, so we have to bound the entropy, and we have something negative, which is this Carré-Duchamp, which is let's say a sort of energy. Okay, and we have an expectation of some function. Okay, so if we can estimate the integral by the energy, and maybe the integral by the energy plus the entropy, then we're in good shape in order to prove a bound for the entropy, because if we can say that this integral, so we forget about the fact that ft is the density of some process. We just say it's just a density, it's just a function with a positive function with integral equal to 1. And now it's a legitimate analysis problem to bound this function by the entropy of f and this energy form given by the Carré-Duchamp. This is just a valid question, and when maybe we can answer it or not. And if we succeed answering this question, then we are going to get a meaningful bound for the entropy h of t. Okay, but on the other hand, you can use also the probabilistic interpretation. Is the expectation of a concrete function. Therefore, if the process we are considering is nice enough, so if we know for some probabilistic arguments how to bound this expectation of this function, then we can also get a meaningful bound for the relative entropy h of t. Okay, so this is something very nice about this Yao inequality, that it has this flexibility. We have the opportunity here to use both analytic and probabilistic arguments in order to get the meaningful bounds. Okay. Second thing that we can discuss is about the function f of t, this capital F of t. So it is a function of psi. So it's completely explicit in principle, okay? Because we have the freedom to choose the most convenient function psi of t, and that could be convenient. Of course, we need some input to guess the right measure mu t and the right base measure nu here, and according to that, our function f is going to be easier to bound or not, the expectation of it. So, and a nice observation is that this function f of t is 0 if and only if the function psi of t solves the Fokker-Planck equation. This is clear because actually what is written inside the brackets, inside the braces here is exactly the Fokker-Planck equation for psi of t. Okay, so if psi of t is actually the law of the Markov chain started at some initial condition, this is equal to 0. So here, with this observation, we recover something which is also true, but maybe not as well known as the fact that entropy decreases in time. So this is something where probably we all know that the relative entropy of the law of a Markov chain with respect to the invariant measure is decreasing in time. But something which probably is a little bit less known is that if you take, instead of the relative entropy with respect to the invariant measure, you take two solutions of the Fokker-Planck equation. That means you take the law of the Markov chain starting from two different states. Then the relative entropy between them is also decreasing in time. It's not that they just decrease when compared with the invariant measure, but they also decrease among them. So it's a stronger property, no? This decrease in time, and this is you can see it as a consequence of Gauss inequality, because this function f is actually 0 if psi of t solves the Fokker-Planck equation. That also hints into what we should try to put as good reference measures mu t. So it's something that should, at least in an approximate way, try to solve the Fokker-Planck equation. Okay, so this is Gauss inequality. It's it's a surprisingly sharp inequality, because for diffusions it's actually an identity. Okay, so there's not less or equal, that's equal. And if you want to have less or equal here, what you have to put there is, instead of this gamma of square root of t, square root of f of t, square root of f of t, is you put gamma of f of t log f of t, and then you have also an identity in the Markov chain. So this is Gauss inequality, and it's going to be our starting point. So we want to get information about the long time behavior of the Markov chain, and the idea is that if we can guess a reference measure nu which is close to the invariant measure, maybe using Gauss inequality you can show that this entropy is bounded, uniformly bounded in time. Okay, of course, here we're talking about finite state Markov chain, so everything is bounded in time. But of course, there is going to be this scaling parameter n, and you probably what you want to get is bounds which do not depend on it. Okay, so this is just Gauss inequality. So let me give you a proof of this inequality, because I think it's instructive, because people always, at least students, they are always puzzled by the fact that, so at the beginning I told you, no, in principle, and you can use any convex function to construct an entropy, but then everybody uses relative entropy. Why not L2 norms or something else? Okay, so if you play around with entropies, then quickly you realize that the ones that are for which you can actually perform the computations are basically the L2 norm and the relative entropy. Okay, well, then if you perform these computations for L2 norms, what is going to happen is that there is let me go back maybe. Here in this expectation, so you see, I can write it in terms of the integral of ft times little ft with respect to mu t. So in this integral here, it appears ft. It does not appear ft log ft. So we want a little log n of room to play around. If you perform the same computation with the L2 norm, what is going to appear here is basically ft minus 1 squared. So we didn't win any little room to play around. So and then if you try to perform these computations with other entropies, with other complex functions, what you are going to find is that the computations get very messy very quickly. And so the proof of this inequality is surprisingly simple. It's based on this lemma here. So there is a 2 somewhere that I forgot. I even have the room for it. So we have this little lemma. So I like to present the proof because the proof is really good. So we start. It's more or less clear that this log v minus log a you can bound it by the mean value theorem. Okay, so it's going to be smaller than b minus a times the derivative somewhere in the middle. And so you say that if b is bigger than a, then you can bound below the denominator by a, which cancels with a above, and you get this bound. Okay, so this is just this little bound here is just the mean value theory for the logarithm. If b is smaller than a, you perform a similar analysis. There are some negative terms that you have to be careful about, but you still get the right answer. And now the trick is to use this inequality that I just proved, instead of using it from a and b, for square root of a and square root of a, and then you get the bound above. So it's a surprisingly simple trick that improves the original bound we got. And that's part of the magic of the logarithm. So with this little lemma, we can prove Gauss inequality. So we start computing, we start doing some computation. So the first thing is that recall that ft does not satisfy Fokker-Planck's equation. What satisfies Fokker-Planck equation is actually ft times psi of t. But then from the Fokker-Planck equation, we can compute the derivative of ft. Okay, it's just using the product rule, and we got this expression. So using this expression, we can just compute h prime of t. And then when you do the derivatives, what you get is the formula there. Okay, so there is this ft times L log ft that has this tendency to pop in, and then the idea is that when you look at ft, L of ft, L of log ft is a sum of a bunch of terms of the form a log b minus log a. Okay, so this is what is on here. So you just check it, and because of the lemma, you can bound this expression. It's a deterministic bound. It means that it's a pointwise bound. Okay, and you rearrange term to get something negative, and you discover that the extra guy is just L of ft. So we have this bound, and now this L of ft, you can pass it to psi by duality, and you get the bound we were looking for. Okay, so this is just a quick proof of Gauss inequality. And And it's a very useful inequality once you start to understand how the law of the Markov chain you're looking at should look like. And so there is another family of inequalities which are very useful when you look at scaling limits of Markov chains, which are these variational estimates. Okay, so when you look at the Markov chain, a classical question is the study of these integrals. No? For example, and this is something people sometimes do, and in fact, it's a very wise thing to do in simulations, is that if you want to compute if you want to compute, for example, the expectation of a function v with respect to the invariant measure, what you can do is to take the Birkhoff sum, average it in time, and by Birkhoff's theorem, that converges to the expectation of function f with respect to the stationary state. Okay, so in practice, okay, so if you really want to run an algorithm, something that works very well is that you can run your algorithm until the mixing time of your Markov chain, and starting from the mixing time, you compute the Birkhoff averages of your observable f of your Markov chain, and that is actually it's an algorithm that converges in a nice way to the expectations of the function. So whenever you want to analyze this type of questions about long-time behavior of Markov chains, it's a good idea to have a way to estimate this type of integrals here. Okay, so a very powerful tool, which is especially well suited for reversible Markov chains, is, but it also valid for the general stationary Markov chains, is what we call the Kivnis-Varadan inequality. Okay, so if you compute the variance, well, assume that these functions v have a mean zero with respect to the invariant measure, okay? Because otherwise, this second moment is actually going to measure the first moment, not the second moment. So if they have mean zero, so you want to compute the variance of this function. So for example, when you do the Birkhoff sum and you want to know how fast the Birkhoff sum converges to the mean, something that you may want to compute is the variance of the Birkhoff sum. Okay, so this theorem here, the Kivnis-Varadan inequality, allows you to go to that to estimate the variance, and the estimate is actually sharp in the case of reversible Markov chains. It's out of the real guy for just a constant factor. So, but I wanted to present it because there is a variational. It's an example of a variational inequality. What do I mean by a variational inequality? Is that it's expressed in terms of a supremum. Okay, so the bound on the variance of this guy is a supremum of that thing that is written here. So actually, when you look at this, and if you know about Gelfand triples, you can identify the supremum there as the dual null. Okay, so if you think about that, the integral of the Carré-Duchamp, so it's a quadratic operator, the Carré-Duchamp, so its integral is a quadratic form. So if you take the square root of a quadratic form, you obtain a null, and at least a semi. And so in this case, in the ergodic setup for Markov chain, is actually a null of the set of mean zero functions. So that thing here that the supremum that is defined here is just the dual norm of the norm derived from the car hydrogen. Okay, so it's the square of the dual norm, in fact, and it can be shown that the CLT, if the function v does not depend on time, then Birkhoff's theorem holds. It converges to its mean, and then when you normalize, it satisfies a CLT, and the variance is actually twice this dual norm. So this bound is out of the best possible value, but just a constant factor of 10, which is a universal factor. Okay, so this is Kipnis-Varadin inequality. It's very useful in many contexts, and it's a first instance where this variational inequalities appear. Okay, so another formula that appears, another variational bound, can be used to obtain exponential moments of these Birkhoff's average integrals of Markov chains. Okay, and it's based on the Feynman-Kac formula. Okay, so the idea is that when you look at the expectation of exponentials of these Birkhoff sums, if you define properly, what you get is the Feynman-Kac semigroup. Okay, so the formula is here. So this is the Feynman-Kac semigroup. And so is defined like this. So it's in terms of these expectations of exponentials of Birkhoff sums, and the Feynman-Kac semigroup is the semigroup associated to operator L plus Vt, where L is the generator of the Markov chain and Vt is the potential that we are integrating. Okay, and after a little bit of analysis, you can find this formula here. So by completeness, I wrote down the proof, but I don't want to enter into that. I just want to comment on the actual bound. So there is something missing here. So sorry about that, but there is. Let me see if I can make room for that. So I forgot a log in front of this guy. Okay, so we have this this variational estimate for exponential moments. Okay, and again, it's a variational formula because it's an estimate which is in terms of a supremum over some functions f. Okay, and one more time, Carré-Duchamp appears there. And notice that this bound is different from the previous one, because in the previous one, the first integral, what appeared was v times f, and now what appears here is v times f squared. Okay, so and here the supremum, different from the previous case, is here. Are functions which has L2 norm equal to 1. Okay, so if you're interested in it, there is a proof here. It's based on the Feynman-Kac's formula, and the idea is that that supremum that is written there is actually the largest eigenvalue of the operator LT. The operator LT, so it's a Markovian operator plus a multiplication operator. Therefore, it's no longer Markovian. So it means that the first eigenvalue of L is 0, but now that you add a potential to this operator, this eigenvalue is no longer 0. Okay, and then what appears there in this estimate is actually the eigenvalue of that operator. Okay, so so here is the proof in case you want to take a look at it. But and this is what I call a companion inequality. Okay, so actually this bound, no, based on Feynman-Kack's formula can be generalized. Okay, so in the previous slides, what I showed you were estimates on which the reference measure was the invariant measure. But as I've been telling you, we don't really know the invariant measure. Okay, so we can just use all this nice machinery in the situation of non-equilibrium stationary states, because we don't know how these non-equilibrium stationary states look like. Okay, so we propose the following replacement for this inequality. So now, in the concept of Gauss inequality, so we have these reference measures mu t, and now we don't need to start our process with invariant measure. We just start from mu0 and use mu t as a reference for the variational formula, and we get this variational formula. So, and there is a square here as well. No, there is no square because there is a square root of f. So the same variational formula holds, but now there is an extra error term, which is given by the expression here. Notice that this expression here is exactly the same that appears in Gauss inequality. Okay, there is a difference here in coming from the fact that now I'm taking the supremum. So there is also there is no t here. So there is a difference because I'm taking the supremum over all functions f, and in Gauss inequality, what appears is the expectation of the function ft with respect to the law of the process. So it's a different thing, but not very different. So what is nice about this inequality is the following thing. Let's say that when you arrive to Gauss inequality, you decide to take the analysis way. So the analysis way means, let's just forget about the fact that the entropy production term is the expectation of a function. Just treat it. We're just going to treat it as if it's, well, an integral with respect to a density. Okay, and work and now do some analysis on top of that and get some bounds. If we decided to take the analysis way in Gauss inequality, it means that we can also use this variational formula here, and here I also forgot the logarithm. We also can use this variational formula here to get estimates, okay? Because if we did the analysis way in Gauss formula, in Gauss inequality, it means that we know how to get rid of this term here. Once we get rid of that term here, what is left is the usual variational problem that we obtain in Markov chains in equilibrium. So So this is what I call the relative entropy method. Okay, so it's in one hand we have Gauss inequality, which is one possible way to obtain a priori bounds on the laws of our Markov chains of interest. Okay, in this particular case of the relative entropy. I was actually is mu t the evolution of mu zero according to the truth? No. Here in this inequality, no. It's just the reference measure you decide to put there. Okay. So if mu t were the true evolution, then what will happen is that the ft term will not be there. So this really gives you the liberty to decide which reference measure mu t are you going to put. Okay. And
I don't know if you can hear me. I'm a bit lost on this.
Yeah.
The formula. Can you hear?
Yes, I can hear.
Yes. No. Yes. So on the left hand side, you start from some mu zero.
Yeah.
And then on the right hand side, you have a soup of f, but you also have the freedom of this mu t. No.
Yes. So
you mean it's true for every choice of mu?
For every choice of mu t, the point is the bound that is best possible when you choose exactly mu t as the evolution of mu zero according to the true dynamics, because in that case the last entropy production term is not there, and the bound is
okay.
best possible. Okay, so if you choose a very bad mu t, what is going to happen is that you will have a very big function ft there in the last term, and then when you take it gets worse and worse because you take the supremum over all f, no, all densities. So if your function ft happens to be very bad, it's that bound, this bound is going to be very bad. But it's a good observation. So the left hand side does not depend on the choice of mu t, but on the right hand side, yes, and that's a measure of the quality of your initial choice. So this is the setting. So this is let's say the general theory, and now let's go back to our particular example of the reaction diffusion model. So let's see how this general theory applies to the reaction diffusion model. Okay, so let's go back to the reaction diffusion model. So here I threw in some definitions, so you somehow you remember what this reaction diffusion model was. So remember that what I just told you, it was general theory of Markov chains. So everything works for any Markov chain. So the only conditions were finite state space and irreducibility. Okay, so irreducibility it's always necessary, but even finite state space is not really necessary. You just at the end of the day, what if everything is summable, you're still okay. If all the quantities in your estimates are finite, then the inequality is still true. So our setup was okay. The state space of our Markov chains was the space of configurations of particles on the discrete torus of size n. Okay, so here as I told you, the discrete torus of size n is just the integer lattice modulo n. So let me call B the canonical basis on it could be on ZD or ZD or also on ZDN. Both sets are abelian groups, so the canonical basis is the same for both. And so this discrete torus, we put graph structure on it by claiming that X and Y are neighbors if the L2 norm, the L1 norm is equal to 1. Okay, so which is the same as saying that the difference between X and Y belongs to the canonical basis. One of the two possible differences, no? So it belongs to plus minus the canonical basis. And so let's keep introducing a little bit of notation because we're going to need to define the generator and the carré de champ. So particles exchanges, the exchange of particles, also these jumps of particles between neighbor sites are encoded into this transformation. So the transformation eta xy. So if you take a configuration of particles eta, then eta xy is going to be a new configuration of particles, which is obtained by exchanging the particles at x and y, and is defined in this way here. And also the particle creation and annihilation can be encoded into this transformation. Okay, so it's the flip transformation. So eta x is obtained from eta just by flipping its value at site x from 0 to 1 or from 1 to 0. So eta xy is what usually is called the Kawasaki transformation, and the eta x is the Glover transformation. And then let's just recall that so we define some creation and annihilation rates. And this creation rate was actually inspired by the CIS model, so it's the rate of infection. And we took it equal to A plus lambda divided by 2D, the sum of eta y or y neighbor to x. So it means that a healthy state becomes infected with rate A, and that with rate lambda divided by 2D, a healthy site is infected by each one of its infected neighbors. And then there's a recovery rate, which I just took equal to 1 minus A. Okay, and then the reaction rate, okay, so is this function Cx of eta. So it's the rate at which you see in this Markov chain a flip at site x. So from 0 to 1 or from 1 to 0. Okay. So and that's why you multiply by these factors 1 minus eta and eta, the creation and the annihilation rates, because you have to have a particle at site x in order to destroy it, and you need to have a hole, an absence of particles at site x in order to create a new particle. And then the generator of the RD model at scale n is given by this formula here. So okay, so you have the first part, which is it's also that you have this is what we call gamma n square L exclusion. So this is the exclusion part of the dynamics. Notice that this first sum is also generator, and the second part is what we call LR, reaction, from reaction dynamics. Okay, so this is the exclusion dynamics, and this one here is the reaction. So this is a generator of our dynamics, and now we have this family of Markov chains parameterized by this parameter n, and each one of these Markov chains is irreducible. They have a stationary state mu as n, and our aim is to understand this stationary state. So we keep going with these with definitions. Okay, so all these definitions that we are going to need later on. So these gradients, also this difference that appears in the expression for the generator, we give a special names to them, because those names will make notation easier later on. So we call nabla xy to this difference, how much the function f changes when you exchange the particles at site x and y, and nabla x of f is how much the function changes when you flip the value of the configuration at site x. Okay, and then the Carré Duchamp associated to the operator ln. So maybe I didn't call it ln here. I forgot to put the n here, which means that I should put an n here and here. Then this this operator gamma n, the Carré Duchamp, is given by this expression there. Okay. So everything is fairly explicit here. And now we want to use this relative entropy method. So in hydrodynamic limits, there are some measures which are important, and are these Bernoulli product measures of density rho. Okay. So if you forget about the reaction part of the dynamics, if you only look at exclusion part of dynamics, you see that the number of particles is preserved by the dynamics. Okay, so particles are neither created nor annihilated. And then you can see that the uniform measure on the set of a given number of particles is reversible with respect to these dynamics, because the rate at which you go from x to y is the same that at which you go from y to x. So they are reversible, which means that these Bernoulli measures have something to do with that, because the condition, so if you condition these Bernoulli measures to a particular number of particles, you get the uniform measure. Okay, so this Bernoulli product, it means that these Bernoulli product measures are invariant under the exclusion dynamics. And the idea in hydrodynamic limits is that the exclusion dynamics happen so fast that at least locally, what you see in small boxes is something very close to these Bernoulli measures. Okay, so and then it means that this Bernoulli measure has they have something to do with the scaling limits of these models. So once we define these Bernoulli measures, we can define some functions f and g. So you see there are a lot of f's in this node. So there is a small f, there is a capital F, and then there is a blackboard f as well. So you have to be careful and try to remember which f is which. So this is a macroscopic, it's called the macroscopic reaction. This function f is a function of the density rho, and it's given by that. So you see what it is, no? So it's basically, it's the, if your process starts at the measured new rho, the function f of rho is what? Is the rate at which particles are created minus the average rate at which particles are annihilated. And just for completeness here, I'm going to define g of rho as the expectation of cx with respect to these functions. Okay, since the dynamics is translation invariant, these functions f and g do not depend on x. And so now I can define what is called the hydrodynamic limit of the RD model. Okay, so remember that at the beginning I was telling you that if you want to look at, if you want to characterize the stationary state, you need to look at observables of the stationary state. Okay, so and what are these observables? Are just functions from omega n to some nice polished space. Okay, so here the polished space that we're going to consider is the space of positive radon measures on torus. Okay, and so I'm going to look at so the random variables that I want to look at are the so-called empirical density of particles. Okay, so this empirical density of particles is a random variable, which is a random measure. Okay, so defined by duality. Okay, what does it mean defined by duality? If I prescribe its action over all continuous functions, I just prescribe the measure, right? But just by Riesz theorem, there is a one-to-one correspondence between these two objects, and it's given by that. So you see what I'm doing there is that I'm just putting mass 1 over n to the d on each occupied side of the discrete torus. And then I'm rescaling down the discrete torus to be a discrete approximation of the continuous torus TD. Okay, so this defines pi n by duality. And what happens is that this guy here satisfies hydrodynamic equation. Okay, so the hydrodynamic equation is this equation here. So it's something that changes from model to model. It depends a little bit on the fine on the fine properties of the model you're looking after, and but it's for this one, the reaction diffusion models is going to be a parabolic equation with a purely parabolic term plus what we call the reaction term. So it's something of the form f of u. So this is why this function f is called the reaction function. And it turns out that this describes, there's a theorem, okay? So, and what this theorem says, it says that if at the beginning, so you put the initial configuration of your reaction diffusion model in such a way that you approximate some measure, okay? So notice that since the number of particles is bounded by 1, if you approximate some measure, this measure necessarily has density with respect to Lebesgue measure, and the density necessarily is bounded between 0 and 1. Okay, so then I can just write this limiting measure as u0 x dx. Okay, so if the random variable pi n, the empirical measure, converges in law to this u0 x dx with respect to mu0 n, which is the initial condition of our reaction diffusion model, then the same is true for any later time t. Okay, so you also have convergence in law, but of the same random variable. But what changes is the measure that you put on the space omega n. So the measure that you put there is the evolution of mu0 under the Markov chain. So that's what we called STN last time. Now remember that STN was the law of the STN of mu was the law of the Markov chain at time t with initial state mu. And now what happens is that you no longer converge to u0, but you converge to ut, where ut is the solution of the hydrodynamic equation that I wrote before with initial condition u0. Okay, so this is what is called the hydrodynamic limit of the reaction diffusion model. So this theorem was first proved by the Massey, Ferrari, and Leibowitz, which were able in dimension 1 to obtain the associated central limit theorem. Okay, so that was in the 80s, and in the 80s there were super powerful methods which took a full advantage of a very particular fact of the simple symmetric exclusion process, which is that the simple symmetric exclusion process is an integrable probability model, meaning that you can actually compute all correlation functions in an explicit way. Okay, and from that fact, you can treat this model in a perturbative way and get bounds on the correlation functions for any number of points. And if you get the right bounds on the correlation functions, you can just prove whatever limit theorem you want. Well, not whatever, but at least the low large numbers and the central limit theorem just by moment computations. Okay, so this is what the massive Rayleigh-Leibowitz did. So it's a very long paper. I think it's 60 or 65 pages. And then when Wu, Papanikolaou, Varadan introduced the entropy method in hydrodynamic limits, they were able to prove this type of theorems for more general systems. And in particular, in the paper of Kinsmith, Ola, and Varadan, there is a note. So if you read this paper, they say, okay, you know, we are going to prove this theorem I just presented here in section 6. So, and then you go to section 6, and there is something like a half-page proof of this theorem, which was basically a roadmap to explain how this theory of hydrodynamic, this new hydrodynamic limits theory may prove this type of things. Okay, so I think this is a good point to make a break. So should we make a small break?
I think a break. Sorry. I think a break is good.
Very good. So let's make a break. We resume in 10 minutes.
Okay.
Very good. Before we start, maybe I should ask for questions, because of course you can always ask questions, but sometimes if you don't ask for them, they don't come.
So maybe I have a question.
Yes.
If you want to, so here it's about hydrodynamic limit. If instead you want to study like fluctuation process at equilibrium, so in that case you will need to guess some nu that approximates the stationary measure. Okay,
Yeah.
but in that case, mu t, if you want to guess, I mean, if nu is a good guess for stationary, then mu t the good guess should be constant nu, no? Or will you do something?
Exactly, and this is exactly what we do for this model.
Okay. Instead, if you want to study hydrodynamic, maybe you want to follow somehow the hydrodynamic limit and put some kind of Bernoulli. That okay, I see.
Exactly.
Okay, thanks.
Okay, so let's go. So we have this theorem. So this theorem tells you the hydrodynamic limit of this model. But in terms of the stationary measure, what does this theorem tell us? Okay, And then we have to think about the large time behavior of this hydrodynamic equation, right? So what's going to happen is that the stationary solutions of this hydrodynamic equation, since we are in finite volume, are just given by the zeros, the stable zeros of the function f. Okay, so that will somehow tell us that the hydrodynamic, the stationary measure should be concentrated on that densities. Okay, so this is exactly what happens, and so let's see how what can we infer from this. So the first thing, that the first observation is that, of course, as you may imagine, I just chose the rates, no, the reaction rate in such a way that there is only one zero on the interval 0, 1. Okay, so the function f has only one zero at the interval 0, 1. It's more or less easy to see, because if you can compute explicitly f, no, because it's just a formula, it's just a expectation with respect to these Bernoulli measures, is very easy to compute, and you get this formula. No, it's 1 minus rho a plus lambda rho minus rho 1 minus a, and you can check so you see that f of 0 is a, f of 1 is minus 1 minus a. So if a is strictly between 0 and 1, which was one of the hypotheses we made on this constant a, then the function f has a 0 on the interval, on the open interval 0, 1, in fact. And so it's and it's only 1 because it's quadratic. So the number of zeros has to be odd, no, because you have to go up and down. And then, and since, so they have to be odd, and there is at least 0, of course, and at most 2, so it has to be 1. So this is exactly 1, 0 on the interval, on the closed interval 0, 1. Moreover, this 0 belongs to the open interval 0, 1, and I'm going to call it rho a star. Okay, and you can see that this is kind of easy to see from general theory of PDEs, that the solution of the hydrodynamic equation converges exponentially fast to 0, or to rho star, as t goes to infinity. Okay, and in whatever norm you want to measure this. Okay, it could be so, for example, in the uniform norm, this is true, and this is always also true in even some C alpha norms, if you want to. And the reason for that is that this operator, because f prime of rho star is strictly negative, has a positive spectral gap, and from there you can conclude that it's actually the convergence is uniformly fast. Okay, so at this at first glance we can conjecture two things about our reaction diffusion model, about our interacting particle system. So the first thing is that the Poincare and log-Sobolev constants should be bounded in N. Okay, because the Poincare and log-Sobolev constants of the equation are bounded in N. You know, the hydrodynamic equation. Okay, and the second is that under the stationary measure, the empirical density of particles should converge to rho star. Okay. This somehow something reasonable to think about. So I want to somehow tell you that so the first thing is not true. Okay, because remember that we don't really know the invariant measure. So the invariant measure is not clear what it is. And it might be that at the scale of the on which this hydrodynamic equation converges to rho star, you're not even close to the invariant measure yet. It could be, we don't know. And it's not clear that the probabilistic Poincaré, so the Poincaré inequality says, to say that the Poincaré inequality holds for the probabilistic model is something which is much more stronger than to say that for the hydrodynamic limit, because at the end of the day, if you think about it, the hydrodynamic limit is a law of large numbers. Being a law of large numbers, it means that we are losing a lot of information about our process in this limiting procedure. And the second one is that actually it's easy to prove. Maybe obvious it was a little bit of a stretch, so maybe I put it here. Not difficult. Okay, so let me prove that. Okay, let me prove that under the stationary state, the empirical density of particles converges to rho star. Okay, and the proof is not very difficult because actually it's more or less contained on the hydrodynamic limit theory. So as I was telling you, if we want to obtain information about the stationary state, we can proceed in this way. So now what we did is that we prove for fixed T that density converges to this profile ut given by the hydrodynamic equation. Now you send T to infinity in the limit and you discover that all profiles converge to rho star. And now you want to invert these two limits, okay? And here you can actually make something simpler because of the following observation is that the nice thing about the space of Radon measures is that compact spaces are very simple to characterize. Okay, so in particular, no matter which probability law you put on the space omega n, the empirical measures are always going to belong to a compact set of the space of measures. Why? Because you have this trivial bound, no? So pi n of f is always smaller or equal than the n infinity norm of f, which means that pi n is tight under mu ss. It's actually tight under any measure that you put on the space omega n. So it's tight under the stationary state, so we can take a limit point. Okay, so let me call u0 bar a limit point. Okay, and let me call n prime the subsequence under which it converges to u0 bar. So now the point is that u0 bar satisfies the hypothesis of the hydrodynamic limit theorem that I showed you before. Because the only hypothesis that were there is where that the sequence of initial conditions converge to something. Here it converges to something that might be random. It doesn't really matter that is if it's random or not. Okay. That means that we can use mu Sn so that we can use the stationary state as initial condition for the theorem. Okay, not mu Sn, but mu Sn prime, because mu Sn prime converges to something. But now is kind of trivial fact, no? Because it converges to u0 bar. Now you let the chain evolve up to time t, the initial condition was the stationary state, so it didn't change. And now you converge to something different. You converge to ut bar, not to u0 bar, which is the evolution of u0 bar under the parabolic equation. Well, this obviously is a contradiction because you have, for the same object, two different limits, unless these two different limits are the same. So what we conclude from this simple argument, that actually this u0 bar guy, that was the limits of that was a limit point of the invariant of the empirical measure under the stationary state, has actually to be concentrated on the stationary solutions of the parabolic equation. For our particular choice of the parameters of the model, there is only one stationary solution. Therefore, we have just convergence to rho star. Okay, so in this particular case, it was pretty much simple to do this step. Okay. Okay, so now that we learned that the stationary state converges to that the empirical measure converges to stationary under the stationary state measure converges to this constant profile rho star. We're going to make a guess. Okay, so we do an educated guess for how should look like this this stationary state. And we say, okay, the only thing from this theorem, the only thing we discovered is that the density is rho star. So we say, okay, at first order or zeroth order or at first order or at some level of, at some degree of approximation, maybe this product measure nu rho star is a good approximation for the stationary state. So that says is okay. So let's use it as a reference measure. Then yes, it seems to be a good idea to use this nu star as a reference measure. And since we are, notice that the situation here is different from hydrodynamic limits. In the hydrodynamic limits, you are given an initial collection of states that converge to some profile u0. Here, we have the freedom to choose the most convenient initial profile for us. And it's more or less clear that the most convenient initial state should be constant, right? Because that's the stationary solution of the parabolic equation. So we choose as initial profile this this product measure, and now what we do is that instead of maybe in another problems you want to do that, you want to take a family of reference measures which depend on time. But here it seems that since we are interested in this in the stationary situation, it seems a good idea to not take advantage of that freedom this time, and to choose just mu t equal to mu0 equal to this product measure nu rho star. So in that case, the ft so psi is equal to 1 in that case. Okay, so all the reference measures are the same. So this function psi in the relative entropy method is just equal to 1. So the function ft does not depend on t, it's just a function f. So this is blackboard f. So pay attention to the different f's that appears all the time. And this function f is just equal to ln star of 1. Remember, the measure nu rho star is not invariant. Therefore, ln star of 1 is not 0. Okay. So then, and the Gauss inequality, what is written there is just like that. So the only difference with the inequality I wrote before is that now the measures don't depend on time, and also the function blackboard f does not depend on time. And then, and now what we have to do is to compute this this function blackboard f. So the measure new row star is invariant under the exclusion part of the dynamics. So we only have to take into account the reaction part of the dynamics. And then, well, you do some computations, no? You put some test functions and you discover that, so by duality, that the Ln star of 1 is equal to this sum here. Okay, so notice that this is an explicit formula because the function new row star is explicit, the rate functions Cx are explicit, so you can just go on and compute it. So after some computations, you discover this. So the function f is equal to the sum of these two terms. So here you see there is already one cancellation. Is that okay? This is something which is always true. Okay, so L star of 1 is not 0, but it's always a mean zero function, right? Because so maybe I can let me see. Yeah, this is my last slide, so I can write here as so what I meant is this also. So this integral is actually equal by duality. So what I do is that I can sneak in here another one. And this is actually equal to 1 times Ln of 1. And this is equal to 0. So the function f that appears there, the blackboard f that appears in the entropy production, is always a mean zero function. Okay, so let's go back here. It's always a mean zero function, so it means that you can always write it as a function of centered variables. Also notice that the reaction terms, the nucleation terms, all these guys are polynomials in the variables eta x, and they are second order polynomials, so the polynomials of degree 2. So it means that the function f is going to be also a polynomial of degree 2 with respect to the variables eta x. So since it has mean zero, I can always write it in terms of the centered variables eta x minus rho star. Okay, so f of eta is a second order polynomial on the variables eta x minus rho star with constant term equal to 0. But actually, so this is true for any reference measure, but since we are taking rho star as the density of the nully product measure, there is an extra cancellation. So the first order term is also equal to 0. Okay, so it is there that we are using the fact that we are looking at the stationary solution of the parabolic equation. And then what we are left with is a second order term. So this is second, I call it second order because it's quadratic in these center variables. Okay, so and here there are two important things that happen is that there is a lambda in front of these guys. Okay, this lambda is going to find against A. Okay, so rho star. So if A is fixed and lambda goes to 0, rho star goes to A, or 1 minus A. Let me see. One has to look. Yeah, A. So rho star goes to A. Okay, so when lambda goes to 0, rho star goes to A, which means that the denominator, at least on a neighborhood of 0, it's bounded about 0. So we don't have to worry about it. But the numerator in principle can be very big. Okay, so what happens here is that this lambda fights against A, and these models, okay, as I was telling you, is an example of a driven diffusive system. Driven diffusive systems are complicated. Okay, so we have a theory, a phenomenological theory of driven diffusive system, which is called the macroscopic fluctuation theory. The macroscopic fluctuation theory describes the large deviations of these models, actually the dynamic large deviations, with rate functionals, which depends on thermodynamic quantities of the model. Okay, so there are some fixed number of parameters that enter into those computations. So if you want to, the large deviations are characterized as functions of the density rho and the parameters of the model A, lambda, and gamma. Okay, and there is a phenomenological theory for that. Macroscopic fluctuation theory presents something which is called dynamical phase transitions. Okay, so what are dynamical phase transitions? So in these models, so the stationary state is a non-equilibrium stationary state. There are currents. And one question that you can ask, which is a natural question, is what is the probability of observing an anomalous current, some current which is different from the natural value of the current? And this is something which is exponentially small, and the rate in the large deviations principle tells you how exponentially small it is. And at the level of we just saw that the stationary state satisfies a lot of large numbers. From hydrodynamic, from the theory of hydrodynamic limits, the machinery used to prove these law of large numbers is actually the same which is needed in order to prove large deviations principles. The actual proof, the whole difficulty in order to get a large deviations principle for these interacting particle systems comes just from the fact that sometimes the large deviations functional is not good. So then you have to work more. So, but the point on that is that you can ask in principle that. So what is what are the probabilities to see something anomalous happening on the stationary state? And this is something you can ask, and macroscopic fluctuation theory tells you how this happens, how this large deviation happens, and also tells you how these large deviations are produced when you look at the trajectory of the model. And there is, and people say that this dynamical phase transition, the following thing happens. So imagine that you ask for a large deviation on the current according to the stationary state. And then you say, well, then the natural thing to do, if you want to produce a current in the stationary state, is to produce the same current at any time t. This is a very natural thing to do. so you can compare the large deviations of, let's say, the bulk of averages with the large deviation of the stationary state, and they should be the same. But in these systems, there is a phase transition because they are not the same. So at some point, what happens is that the most efficient way to create a current in the bulk of sum is not to create a current and maintain it constant in time, but to oscillate. This is something that might happen, might or might not happen. So it's more efficient from the point of view of large deviations to make the current oscillates between two values in such a way that when you average, you get the current that you want, than to fix the current at the value that you want. And this is reflected on these computations that we are doing here. Okay, so what I'm going to present tomorrow, now this is probably going to, this is what I want to do tomorrow, is that I want to build on this relative entropy method to prove the CLT for the stationary state. Okay, so a central limit theorem for mu SS, and our result is perturbative. So it only works for lambda small enough. And the reason for that is that is somehow related to this question that I mentioned, that this thing that is actually not, I don't know if it's really true, but I suspect it's not true, that the Poincaré constant and the log Sobolev constants are finite. Because, so lambda, this constant lambda is if you increase lambda, what happens is that the model, the entropy production increases. So this function f is bigger. So the positive term in the Yau inequality is bigger. But if you increase lambda, the Carré-Duchamp doesn't change. At least not in a meaningful way. Okay, so because the lambda only allows you to create particles, but not to destroy particles. So it doesn't help you to equilibrate the system faster. Because if you want to somehow mix your system, lambda is not helping you, because okay, it's helping you in one direction but not in the other. So it helps you to create particles, but then you want to destroy them back, and it's only done by the constant A. So there is a fight between lambda and A, and this fight sometimes is won by A and sometimes is won by lambda. Okay, so that means that it doesn't mean that our result that the CLT is not going to be true for any lambda, but it means that there is an obstruction. And this obstruction is meaningful because we know that at least at the level of large deviations, big lambda is bad. So there is this fight, which here you can see it already from the formulas. It's of course not a proof that big lambda wins over A, but is at least an indicator that in order to treat big lambdas, you need something else, something out of the general theory that we're building. Okay, so so this was my last slide. I think I went a little bit faster than I thought. So maybe I just stop here and open for more questions if you haven't. So please ask questions, and you can ask also questions about the pictures if you're really not in the mood to mathematical questions. But please go ahead and ask whatever questions you whatever doubts or thoughts you may have.
So,
yes.
Yeah, I have a question, actually, too, maybe. So you mentioned, so the CLT you will discuss tomorrow. You mean CLT under the stationary measure or CLT for like space-time?
Under the stationary measure.
Okay.
So space-time CLT, let me see. So the space-time CLT is proof in a paper that we with Ottavio. But there the estimates were not good enough to go to the stationary measure. So it's so that requires an extra argument. And this is basically what I wanted to discuss tomorrow.
Okay, so you're saying the CLT under the stationary measure is harder than, or did that?
Yeah, exactly. Okay. So the CLT under the stationary measure is harder than the space-time CLT under the, let's say, starting from new row.
Okay. But yeah, and you can also do space-time CLT starting from stationary. That should be more than no.
No, okay, yeah, okay. So once you have the CLT for the stationary measure, the non-stationary CLT basically covers that case. It's like then it's just a small argument that I made about the hydrodynamic limit. No, so if you can prove hydrodynamic limit for a wide range of initial conditions, then you just have to show that the stationary state satisfy the initial conditions. The hypothesis for so you need to prove that the stationary state satisfies the hypothesis you need for the initial conditions, and then you have the stationary CLT, the stationary space-time CLT. But the difficult part is to so if you want to prove the space-time CLT starting from the stationary measure, the hardest part is to prove the CLT for the stationary measure.
Okay. I had also another question. So if you go to the previous slide, maybe. Yes. So here, just to be sure. So here, H is the relative entropy with respect to the nu, no? Or
exactly.
So it started at 0. So H of 0 is 0.
H of 0 is 0.
Okay.
Exactly.
And then maybe you are able to say that somehow the two terms on the right, I mean this, okay, so eventually for t going to infinity, this just converges to the relative entropy of the true thing with respect to nu, so it converges to something.
Yeah.
Positive. Okay, so if you are able to say that this is not growing too much, so can you deduce in a quantitative way that nu was close enough to the true one? Or
yes. In fact, so how it goes. So then from this you can say, okay, for example, let's think about dimension 1. Yeah, just to which is simpler. So in dimension 1, we can prove that this h of t converts to a number. Okay, so it's bounded uniformly in t and n. Okay, so it means at the end of the day that the fluctuations. So if you look at the CLT, so if you look at the limiting law, the limiting law of the fluctuations of the empirical measure is absolutely continuous with respect to white noise. So this is something that we can prove because it's a consequence of the fact that the entropy is bounded in T and N. It's bounded in everything. And then we can also characterize it. No? So we can say, no, actually, it is this particular Gaussian process that it is indeed absolutely continuous with respect to white noise. And so once you have done that, you can be more ambitious and say, okay, Now that I know the limit, I can make a better guess for the stationary state. Okay, so and this is basically this estimate in the thesis of Benoit Dagalier, no? That once you discover what is the Gaussian process that goes there, you can use that to construct a measure with the right 2-point correlations, and now you get a better approximation. Once you have done that, you can be more ambitious as well. So here this looks a lot like a renormalization. So you see, so you do the hydrodynamic limit, so it's like a 0th order approximation, and then you get a 0th order approximation of the process. So something that covers the first the 1-point correlations. Okay, so it's just expectations of your variables. With that, you can go and obtain the CLT. The CLT gives you the 2-point correlation functions. And now you can go back to your model and construct a measure that coincides with the invariant measure up to the 2-point correlation function. Once you have done that, in principle, you can iterate. And so you can keep doing this, and in principle, that it could allow you to get as close as you want to the stationary state. But maybe you don't want to go beyond the CLT, no?
Okay.
But and for example, in higher dimensions, we what we do works up to dimension 3. Okay, so in dimension 3, we get a bound on the entropy which is like of order n. Okay, which is bad, no, in a sense. But even though it is growing with n, it is good enough to allow us to prove the CLT.
Okay. Thanks.
Can I ask also just around what you said? So this sounds a bit what you just discussed, that the stationary measure, at least in this one-dimensional case, to leading order looks, I mean, you have this, I mean, they are IID, or is that correct? I mean, that you don't have much correlation. They're basically independent, at least in this limit.
No, actually, no.
No?
No. What happens is that, so our theorem, actually what we prove is that under the stationary measure, this that the CLT is given by white noise plus an independent Gaussian free field. And in dimension 1, the GFF is a function.
I see. So,
and then what happens in white noise, you can get a function for free, basically, no? Because adding a function is absolutely continuous with respect to white noise, because what you can do is just you move the mean of the Gaussians, basically, to get whatever function you want. So it's a tilt of so tilting the Gaussians, you get any function you want. So and the funny thing is that the Gaussian free field has long range correlations. So you do get something with long range correlations.
Does that have to do with the fact that sort of to leading order, you have two noise components? One is the derivative of white noise and one is the white noise. And for the SPDE with the white noise, you would get the Gaussian free field as the Gaussian component. And for the other one, you would get white noise.
Yeah, basically yes. It's a little bit more miraculous than that, but it is basically that. Because okay, there is some algebra there is some miracle, because okay, so is a massive free field, what you get.
Okay.
Okay, so what you said is true. So you have two independent noises, and one of them wants to give you a white noise. The other one wants to give you free field.
Mm-hmm.
But they interact because of the equation,
mm-hmm.
and that interaction at the end of the day gives you a massive free field.
Okay. And the interaction is your reaction term.
Is a reaction time, yeah.
Okay. Very interesting. So I think,
yeah.
I think there are perhaps no more questions, or if you want us to say something, otherwise we can say thanks. I mean, it's
okay.
Or Fabio, did you want to ask something?
No, it was a thanks.
Okay. Okay, so thank you very much, Milton, and okay. And